conditionalism, a case for second-order logic, vagueness in context, and varieties of logic just to mention few names. In addition, he has authored several influential papers on the aforementioned subjects. Currently, he is honorary professor of philosophy at the Ohio State University and honorary professor at the University of Scotland. Today, he's going to talk about points, boundaries, and context. So, without further ado, welcome, Professor Shapiro.
Thank you. Thank you. It's a delight to be here. It's my first time in Mexico to speak of, other than like 45 minutes in Tijuana. About 10 years ago, or it's very different. It's a delight to be here, and I'm sort of looking forward to seeing more. This talk is a part of a larger project that I'm on with Jeffrey Hellman on the notion of continuity. We both got interested in it some years ago, and that led us to Aristotle and to the relationship between points and the continuous. And we began developing, we're not the first ones to do this, of course, but we've been developing an account of the continuous that doesn't see continuous things as composed of points. And then I kind of noticed, or I did more than him, that a lot of contemporary metaphysicians get themselves all tied up into knots as to what to say about points. And if you don't think of continuous things as composed of points, those issues are really non-issues. So what I want to do in this talk is, about half of it, I'm going to give you a very, very brief overview of Aristotle, at least some important parts of Aristotle's accounts of the continuous and how it differs from the kind of orthodoxy today, the Dedekind-Cantor one, where you're thinking of, say, a line is just a set of points. And then that'll take about half the talk, and then the other half will get into the metaphysics, and I think some of the sort of crazy knots that those folks get themselves all tied up into. All right, so so the Aristotle versus the New Orthodoxy. The Dedekind-Cantor account is it's sort of the one you all learned when you were in high school, that that a line is just a set of points. There's infinitely many of them. It's uncountably many. That's sometimes called the classical account because the logic is classical, but I don't like using that phrase because we're sort of contrasting that one with Aristotle. Right? So if anybody gets to be classical, so I changed the word again. Even the orthodox, right, should be the older thing. So I'll call it the old orthodoxy versus the new orthodoxy. And I understand that there are a couple of ancient philosophers here, and that kind of scares me because I don't really know what I'm talking about. But we'll do my best, and I don't mind getting corrected. I have actually discussed this with a few ancient philosophers. All right. So first of all, common ground between the Aristotelian account and the contemporary orthodoxy. So in some ways, Aristotle came remarkably close to the contemporary account, the so-called classical conception. I never got the slides quite right. I'm kind of new to writing in tech and writing slides, and so there's bits of this that I had to do this in a hurry, as I always do, and so it didn't always work out right. Trace to Cantor and Dedekind, and it's especially in comparison with Aristotle's main opponents. Now, there wasn't anybody in antiquity who represented what's the contemporary view for reasons that had to do with infinity. But Aristotle's main opponents were on the other side of the stream. Those were the atomists, who thought that there really aren't any continuous substances, that there's like a smallest size. Okay. So, all right, so first of all, for Aristotle, so this is common ground between the contemporary account and Aristotle, as opposed to Aristotle's main opponents. A continuum is infinitely divisible in the sense that it has no smallest parts. That's the main thing that the atomists rejected, at least some of them. Sticking to one dimension, the idea is that any line segment can be bisected any number of times. And the results of a bisection are two bisections, and you could bisect those indefinitely. So that's the one piece of common ground. And the second is that Aristotle's continuum is Archimedean. And this has two formulations. And this is me, it's not a quote. Let A and B be two finite magnitudes of the same direction, say 2 line segments. Then there's a natural number m such that the result of adding A to itself m times, m times is bigger than B. So you can get from any size to bigger than any other one in a finite number of times, right? So there aren't any infinitesimals. So you sort of, everything's infinitely divisible, but not so much that they're infinitesimals. So now here's Aristotle. By continually adding to a finite quantity, I shall exceed any definite quantity. Right? That's the Archimedean principle. By adding to one, I can surpass any other one. In Euclid, now Euclid of course came a bit after Aristotle, but it's generally agreed that all of the mathematics at the time of Euclid were all available to Aristotle and Plato, and they were all sort of, and they had all bought it. Right. Unlike the opponents, the atomists, who didn't buy the geometry at the time. All right, so in Euclid, the Archimedean principle is kind of a definition. Magnitudes are said to have a ratio to one another. That's what he's defining, what it is for 2 magnitudes to be in ratio, which are capable when multiplied of exceeding one another. Yeah, same idea. Take the smaller one, multiply it enough times, and you'll be bigger than the bigger one. The second one, so that's the first formulation of the Archimedean property. It has to do with getting things bigger. The second one has to do with getting things smaller. So if you start with 2 finite magnitudes and take the bigger one and take away at least half of it, and then take away at least half of that, and then half of that, and half of that, and so on, eventually you'll get something that's smaller than the other one. Right? Now the ancient Greek mathematicians made brilliant use of this. The method of exhaustion, right, all sort of ties on this, and they were able to use this to figure out the areas of curved figures and stuff like that. All right, so here's Euclid on the same thing. I couldn't get this all on one slide, mostly because I hadn't quite figured out how to do slides yet. 2 unequal magnitudes being set out. If from the greater there be subtracted a magnitude greater than its half, and from that which is left a magnitude greater than its half, and if this process is repeated continually, there will be left some magnitude less than the lesser magnitude set out, right, smaller than the other. Now Euclid proves this from the first Archimedean principle, that is the definition, and using also some properties of unequal magnitudes. All right, so I mentioned the method of exhaustion already. All right, so that's common ground. So the common ground between the contemporary Dedekind-Cantor account and the ancient one, the Aristotelian one, is infinite divisibility and the Archimedean property. The differences, of course, are more important for us today. To put it anachronistically, Aristotle argues that, so Aristotle made an argument at the time that everybody in this debate seems to have bought. And the argument is that time, space, and motion all have the same structure. And Aristotle and his opponents all agree to this. The idea is that, well, the argument is that since motion just is movement in time through space, right? So if one of these is composed of points, then so are the other 2. If one of them is not, if the atomists are right about one of them, then the atomists are right about all 3. And if the Euclideans or Aristotelians are right about one of them, then they're right about all 3. So all 3 have the same structure: time, space, and motion. All right, so if one of those is punctiform, that is, if it's composed of points, then so are the other ones. Or if one is composed of atoms, so are the others, and so on. All right. Contemporary metaphysicians haven't bought this, but sometimes they'll talk about time being one way and space being a different way. All right, now, probably the most central feature of the Aristotelian account is that continua, concerning all 3, time, space, and motion, are not composed of points. So for continua are not punctiform. That's just another phrase for being composed of points. The parts of a line segment, then, all right, so for Aristotle, as for Euclid, lines are always lines, what we call line segments today, right? No infinitely long lines. But, so the parts of a line segment are just other line segments. In the jargon of contemporary metaphysics, continua for Aristotle are donkey, right? No smallest part. All right. Now Michael White attributes the following principle of non-supervenience to Aristotle. And here's sort of part of the argument why Aristotle thinks that continua can't be composed of points. Each partition of a that's a typo. Each partition of a continuous magnitude into proper parts yields parts, each of which is pairwise continuous with at least one other part. So the principle that Aristotle is putting forward here is that if you have a continuous thing, say a line or a chunk of space or something, and you divide it up into parts, any two of those, any one of those parts will be next to another one. That's what he means by continuous. You don't get that in the Dedekind-Cantor account. Right? You divide up a line into points, right? It's not the case that each of those points is next to another one. Right? So for Aristotle, as for Euclid, as for the contemporary mathematicians, between any 2 points there's a line segment. Right? So there won't be a point next to it. Right? Now, so as Aristotle puts it, that which is intermediate between points is always a line, and that which is intermediate between moments is a period of time. The word moments there, again, I don't know Greek, but the word that he uses for moments is actually now, and it's sometimes translated that way. He calls them like an instant in time, a now. But a moment is, I think, a better, at least, So so by the principle of non-supervenience, no 2 points can be continuous. No 2 points can be continuous with each other. So it follows from the principle of non-supervenience that you can't divide up a line, you can't partition a line into points, into point-sized pieces. And this, of course, is where Aristotle parts company with the contemporary. Well, the anachronism put it that way. You can't part company if you didn't know them. But this is where the Aristotelian parts company with the contemporary Dedekind-Cantor. Right now, Aristotle, though, unlike some of the more modern gunky accounts of space and space-time, does recognize points. And points are crucial to his views on continuity and indecomposability. We won't get to indecomposability, but they're crucial to his views on continuity. First and foremost, for Aristotle, points are the limits or endpoints of line segments. So it isn't that a line is composed of points. All a point is the end point of is the end of a line segment. So each line segment will have 2 endpoints. That's first and foremost. That's sort of the primary definition. So each point is somehow metaphysically tied to the line segment that it's a point of. Now there are points interior to a line too, but those only exist potentially, not actually. So if you take a line segment and look at a point inside of it, say the midpoint, that's a place where the line could be divided. Right? That's why it exists only potentially. But unless the line is divided there, if you bisect it, all the Euclid say, then that point doesn't exist. It's only there potentially. Right. Now, and Aristotle sort of comes to this, well, there's a bit of dispute among scholars here, and if they have disputes, then I'm not allowed to have an opinion. But most of them think that Aristotle comes to this view of points because he's thinking about Zeno's paradoxes, right, which sort of rock the ancient world out there. So here's one of them. So consider an instance of Zeno's paradox of division. Suppose that you have someone, Ms. Walker, she wishes to cover a distance of 100 meters. All right, now go from here. All right, now before she can do that, she has to cover half that distance. So she has to walk 50 meters first. Call that walk 1. She has to take walk 1 first. Then she has to walk the next 25 meters. Walk 2. Call that walk 2. Then the next 12.5 meters, like walk 3, and so on. Right? So then Zeno concludes that in order to reach her destination, she has to do an infinite number of walks. And Zeno concludes from that she can't do that, and so the motion is impossible. This isn't the first time, you have a philosopher, well, it probably is one of the first times, but there have been a lot of times since then where a philosopher sort of tells you something that we know from common sense is, So he says motion is impossible, change is impossible, right? It's all an illusion. Now, of course, Aristotle, unlike Plato, is really going to be the defender, for the most part, of common sense, so he's going to have to find something wrong with this argument. We find something wrong with it today, too, but not the same thing that Aristotle found wrong with it. All right, so Aristotle, of course, follows common sense, and he disagrees with Zeno's conclusion. And his view on points that I sketched before plays a central role in that, right? And so what's wrong with Zeno's reasoning? Consider the endpoint of walk 1, right? So remember, Ms. Walker starts off and goes 50 meters, and we call that walk 1. And consider the point there, right, in space where she stops. Or no, sorry, I gave it away. Consider the point at the end of the 50 meters. That's a place where she could stop, where she could pause her journey, either temporarily or permanently. That's what it means to say that the point exists potentially. She could stop there. And there are infinitely many places Aristotle recognizes where she could stop, right, in anywhere along the 100 meters. But unless she does stop there or somewhere else, there's no separate walk 1 to consider. There's just the single event, the 100 meters, the walk of 100 meters. That walk is not the sum of walk 1, walk 2, walk 3, and so on. All right, so that's the one difference. Now I realize there are versions of Zeno's paradoxes that this doesn't solve, that Aristotle didn't know about those, and Zeno didn't either. We can get to that later if anybody wants. All right. So that's one. So that's Aristotle on points. Next is Aristotle on continuity and contiguity. So that's a distinction he makes between the contiguous and the continuous. I don't know if there's. I mean, that's a distinction. In English, those are more or less synonyms, but it's a translation of two Greek words that it's a distinction Aristotle's making, right? He's just using the two words, right, to make it. So here it's the discrete from the continuous. It's that distinction, right? So discrete are number and language. Continuous are lines, surfaces, bodies, and also besides these, time and place. Remember, time, space, and motion are all going to have the same structure. Right? For the parts at which, so let's go back to number. Now for number for Aristotle is always number of something, right? And it's a natural number here, like 5 or 12 or something. But it's going to be not a number as a Platonic entity. I mean, Aristotle wasn't a Platonist, right? But it's always numbers of things, right? So it would be number of sheep, number of people, right? All right, so when he says number, it always means number of something. So the parts of number, say 5 sheep, have no common boundary at which they join together. Right? You just have the 5 sheep. Right? Nor could you ever, in the case of number, find a common boundary of its parts, but they're always separate. Right? Say the people in this room, they're always separate. Now, of course, they could be touching, holding hands or something, but they don't have to. Hence, number is one of those discrete quantities. So number is on the discrete side. Similarly, language, this is interesting, is also one of the discrete quantities. Now, by language, he means spoken language here. For its parts do not join together at any common boundary. For there is no common boundary at which the syllables join together. Each is separate in itself. Right? That's discrete. Now we do continuous. A line, on the other hand, is a continuous quantity. For it is possible to find a common boundary at which its parts join together. Remember, so if you take 2 line segments that are next to each other, right, there is a common boundary where they join together. The point, right? There's a point there that's the left endpoint of the one of them and the right endpoint of the other one. All right, so I already did this about numbers are always numbers of things, and a line is what we think of as a line segment. So when 2 segments join together, there's a common boundary. Right, the point, right, that connects them. Right, now here's a bit of contiguity. In Book 5 of the Physics, he defines 2 things to be contiguous if they're next to each other in such a way that nothing can be between them. Right, so things are said to be in contact. That's another phrase for contiguous, in contact, that he uses. Right? Things are said to be in contact when their extremities are together. Right, so I've checked this with my main source on this when I get into this stuff on Aristotle, especially when logicians tell me that I'm getting it wrong, is I talked to my colleague at St. Andrews, Sarah Brody, and she liked this example. So think of a pair of books adjacent books on a tightly packed shelf, as an example of things in contact or contiguous. They're so close together that nothing can get between them. But there's still 2 of them. That's why it's contiguous. Right, and a thing is in succession when it is after. Oh, I don't think we need this. Okay. All right. So 2 things are in succession if they're in one after another, and nothing of the same kind can be between them. Right, that's what this quote is. 2 things are contiguous if they're one after the other, and nothing is between them. So if you think of like a row of houses, right, on a street, right, those would be in succession because there's no houses between, neighboring ones. But but they're not contiguous because there is space, well, at least, depending on how the street is. But, if there's like a yard or something between them, then they're not contiguous. They're contiguous if nothing is between them, can't get between them. Okay, now he goes on to define what's continuous, right? The target, the thing we're after. So he defines it as a relation between two things. The continuous is just what is contiguous, that is this property of being next to each other with nothing to get between. But I say that a thing is continuous when the extremities at which they are in contact become one and the same, and are, as the name implies, contained in each other. So things are continuous with each other when they come next to each other. The boundary disappears and becomes merely potential. So this definition, so getting back to Aristotle, this definition makes it plain that continuity belongs to things that naturally, in virtue of their mutual contact, form a unity. So if something's continuous, then it's naturally a unit. There's something holding it together. That's also something we don't have in the contemporary account. Right? A line just is a set of points. There's nothing holding them together. Right? No unity there. All right, so the aforementioned books, right, on a shelf, right, are not continuous, because no matter how close they get to each other, right, each one has its own boundary. Right? The boundary of this one is different from the boundary of the other one. Even when contiguous, they remain two books. In contrast, when two continuous things, such as line segments, come into contact, the boundary between them is absorbed and they become a single line. Now, Sarah liked it. This is my example. I'm kind of proud of it. Sarah liked it. For a more physical, Sarah Brody, that is, probably one of the foremost Aristotle scholars in the world. So I think this is kind of cool. So if somebody tells me I got it wrong, I'm great. So for a more physical example, think of what happens when you leave two chunks of wet dough to rise before being baked into bread. This happens to me all the time. It used to happen when I used to bake bread. When you put them down to rise, and you leave them too close together. Right? So then they rise until they come into where they're contiguous with each other. But then the boundary disappears, and they become one loaf. Right? All right, now in book 6 of the Physics, Aristotle summarizes these definitions and sounds the themes that motivates, the present project. I don't mean the one I want to talk about today, but the one with Helmut. Now, if the terms continuous in contact, or contiguous, and in succession are understood as defined above, things being continuous if their extremities are one, right? That's the wet dough, or the line segments. In contact if their extremities are together, right? The books. And in succession if there's nothing of their own kind intervening between them. Nothing that is continuous can be composed of indivisibles. Right? That's the conclusion. Nothing that is continuous, where its parts are continuous with each other, can be composed of indivisible things like points. They all have to be gunky, right, in the contemporary metaphysical sense. A line cannot be composed of points, the line being continuous and the point indivisible. One other thing, again, I'm not a scholar here, maybe some of you are that can help me, but I don't know why Aristotle would bother saying this, because I don't know of anybody in the ancient world that held that. Right? I mean, if Dedekind and Cantor had sort of gone back in time and were hanging around and doing it, then he would have had an opponent, right? But no one held this, but Aristotle, again, is making a big deal of it. It could be that Zeno's kind of supposing it, or he's sort of attributing a view like that to Zeno, or he's claiming that that's Zeno's mistake, right, or something like that. But again, that's not, so much for present concern. All right, so if these views on continuity, so it's these views on continuity, all right, so I'll just summarize this. So a common theme about continuous things that is lost on that we don't have on the Dedekind-Cantor account is that continuous things can't be broken up cleanly into parts. And Aristotle holds that but for different reasons than others do, say the modern intuitionists. For Aristotle, if you take something continuous and break it into parts, you're actually creating something new, or actually two new things. So if I take a line and break it up, I'm creating two new things, the two endpoints. Right? For most contemporary people, like the intuitionists who hold a similar view to this, when you break it up, you lose something. The way they put it is that when you cut it, something will stick to the knife. Right? But for Aristotle, you're also getting that it can't be broken up cleanly, but for different reasons. Or think about the wet dough. If you break it, if you sort of take a loaf and break it in half, you're creating two new things, the two new surfaces. Okay. All right, so this is a summary. For as soon as bodies come into contact or divided, the boundaries simultaneously become one if they touch. That's if they're continuous. So the boundaries become one if they touch and two if they're divided. Hence, when the body's been put together, one boundary does not exist, but has ceased to exist. And when they've been divided, the boundaries exist which did not exist before. Right? The boundaries were only there potentially. Okay, Don, we don't need to get into Aristotle stuff on infinity because it's a distraction and not so relevant here. But I mean, well, it's relevant to the Aristotle thing because he doesn't think that there are any actually infinite sets. That's another thing that we don't have today with the Dedekind counter count. You're thinking of the line as an actual infinity of points. Right? So these are obviously connected, but now what I need to do is get to the other slides. So now let's show my dexterity with Max. All right, same title, but different color. Right, now switch gears. Now we're sort of on contemporary the analytic metaphysics. Okay, how am I doing on time? All right, so about right, about halfway. Okay, good. That's perfect. Okay. All right, so now contemporary analytic metaphysicians have occupied themselves with the nature of, or the possible nature of space and time, and with the relationship between physical objects and the regions of space or time they occupy. Some of the issues concern the boundaries of objects and the notion of contact, and that's sort of a big topic there. Much but not all, but most of it, the literature, the metaphysical literature, just assumes the Dedekind counter account of space. Right? They just assume that space is composed of points, and then they kind of wonder what do we have to do about point-sized objects and stuff like that. Many authors get tangled up over what to say about point-sized regions, like points in space, that is, and even point-sized objects, as we'll see. The purpose of this paper, of this rest of the talk, is to give a somewhat biased overview of some of this literature. I've been told by people who don't like it that it's not the best of it, but that's just the way it is with nobody likes whatever, you know. That's right. All right, arguing that many of the issues are much easier to negotiate if we assume a more Aristotelian account of space. It isn't that you can't define points, you can. I mean, as we know, you can always take an Aristotelian account and put the points in as limits. Right? So it isn't like you're losing anything by doing this. And well, I don't know if we will today, but we'll also briefly broach the question of whether space or space-time really is punctiform. I don't know if I'm willing to defend this, but I think that that's a verbal dispute. But again, we sort of talked a lot about verbal disputes at the first talk, so but we probably won't get to it. All right, now, first of all, what's going on in the metaphysical literature? What exactly are they talking about? Right now, most metaphysicians are aware of the fact that physical objects in the actual world, if there are any, do not have the sort of boundaries envisioned in their metaphysical theorizing. And they know that the world isn't like that, like what they're envisioning. They know, at least when they were in college, they took some physics, and so they know that objects don't have sharp boundaries, if they knew any quantum mechanics, and they know about repulsive forces that keeps objects from actually touching and stuff like that, right? But still, all right. So now, what are they doing? Now, some of it, right? Well, I think that's an interesting question, right? And sometimes they address it. Some of it takes itself to be exploring logical space. That is, they're asking what boundaries of contact are like, or would be like, in those possible worlds where physical objects do have precise locations, and where objects do come into contact with each other. As noted, members of this group, most of them anyway, are fully aware that the actual world is not one of those worlds, but they profess interest in these other worlds. Or better, a more sober way to put it is that they're interested in logical relationships between various theses. This is charitable, right? All right, now, a second orientation is, all right, so that's the first one, it's sort of exploring logical space, right, for this metaphysics project. The second one is that our questions are addressed in what Strawson calls descriptive metaphysics. So this is the project of, quote, capturing the actual structure of our thought about the world. Right? So they know that the world isn't that way, but how do we think about the world? Right? Descriptive metaphysics aims to, quote, this is Strawson, to lay bare the most general features of our conceptual structure and not to revise this conceptual structure, and presumably not to figure out how the world really is. Right? now whose thought are they talking about here? Whose conceptual structure is the descriptive metaphysician after? As above, it's not that of the scientist or the scientifically informed layperson. Certainly not Maddie's second philosopher. I mean, that character, that character uses whatever she can get from all of the sciences to try to figure out what the world is like. The descriptive metaphysician isn't doing that. So what is he doing? Figuring out what our thought is. Like, how do we think about the world? What's our conceptual scheme? Right? The everyday one, not the one that we get from our science classes, assuming that there is such a thing. Now, John Hawthorne presents a thought experiment, I won't go into it too much, involving an infinite series of walls placed parallel to each other in a finite amount of space. So it's kind of a Zeno type thing. You got one wall here and then another one that's half as thin, but a little space between them, another one that's a quarter thin, space between them, and so on. So there's infinitely many. And so all but a few of the walls are really thin, really thin. But then he anticipates, and then he kind of does this thought experiment. Well, if you kind of walk up to this thing, what keeps you from bashing into it? Right, puzzle, right? All right. Now, then he notes that some people may complain that this isn't really all that interesting. Some may complain that the world he's talking about here, the situation, is too distant to be worth being interested in. Actual walls do have extra repulsive forces, don't get to be rigid and impenetrable in any thickness, and so on. So some people might claim, well, that just can't happen in this world, so why are we bothering with it? Such a reaction is far too hasty, Hawthorne says. Distant worlds can often be either revealing or therapeutic with regard to our actual conceptual scheme. So the idea is that you can, by thinking about those things, we can figure out how we think, whoever we is. Right? To me, this is one of the most wrong-headed things that's ever been written in philosophy. Right. So that's sort of combining the two approaches. Sort of by thinking about logical space, these sort of really wacky worlds, then we learn what our conceptual scheme is like. Okay. All right. So anyway, that's the preliminary, right? What their sorts of questions they're up to. They're usually not all that explicit about it. Right? Hawthorne is one of the more usual ones who is sort of upfront about it. All right. So now our first batch of questions concerns boundaries and contact. So it's common to define a receptacle. This is a technical term. A chunk of space. I should, and I don't want to keep saying space or space-time. So I'm just going to use space from now on. But if you can do this four-dimensionally if you want, it's not going to change anything. So a receptacle is a chunk of space that a physical object can exactly occupy. So our first and primary question, in this branch of metaphysics, concerns just which chunks of space are receptacles. Now, on a regions-based account of space, an Aristotelian one, a natural thesis would be that any region is a receptacle, or maybe. Or if you don't want, that would certainly make sense for Aristotle, because he just thinks of region just as the things that occupy, the chunks of space that objects can occupy. If you don't want scattered regions, then don't allow those. But all this could be. So a natural answer to this, from the Aristotelian point of view, is that any region is a receptacle. But now on the more standard Dedekind and Cantor accounts, regions just are sets of points. So the task at hand is to figure out which sets of points are receptacles, right? Which sets of points can contain objects. Once we decide or figure out what receptacles are, then we have to have something to say about what the boundaries of objects are, if they have boundaries, and what it is for objects to be in contact with each other. So that's the game, right? Now think in sort of Dedekind and Cantor, as we all do, right? Dedekind and Cantor world, where all we have is sets of points. Can we really make physical sense of, say, two ice cubes? One that contains its boundary and one that doesn't. So if you know a little math, one is open and one is closed. Can you really think that there are two different ones? One has its boundary, one doesn't. Aristotle, obviously that would be silly. The boundaries aren't really separate from the thing, right? But again, from the Dedekind and Cantor point of view, maybe that's a legitimate question, right? Well, perhaps there are different kinds of objects, some of which contain their boundaries and some which don't. Right? Questions like these become pressing if you think of space as composed of points in the now standard Dedekind and Cantor manner. Now Hudson, so he's my first target, he argues that any non-empty set of points can be a receptacle. This is the most radical and crazy. Thus he envisions point-centered objects. So he envisions it's possible that there can be an object which is a point, or occupies a point in space. Scattered scattered objects whose receptacles are finite or countably infinite sets of points, objects in free space that are plain squares, and so on. And so he envisions objects whose receptacles are open and some whose receptacles are closed. Right? So he does have, in his metaphysics, the possibility of the open cube and the closed one. And then he goes on to try to figure out what it is for objects to be in contact. And he goes through a bunch of thought experiments and he comes up with this definition here. The idea is that one object touches another one, just in case there's two regions. The first one occupies the first region, the second one occupies the second region. There's a point in the first region, a point in the second region, and there's a boundary point of each of those regions, and the boundary point belongs to exactly one of the objects. Right. So two open cubes, well, we'll get to that. Right. But anyway, it doesn't matter, the EOs, that don't matter. All right, then he articulates a knot. Now that's his phrase, right? So again, I'm not attributing to this to him, this is what he says. He articulates a knot for which he has no satisfying resolution by his own lights. So again, you don't have to really digest it as a kind of contact. I'll go over the relevant bits of it in a second. All right, so notice first that on Hudson's view, certain kinds of objects simply can't touch each other. All right, so think about, so we had an ice cube that doesn't include its boundary, and take another ice cube that also doesn't include its boundary. Right? Those two cannot touch each other. Because in order to touch each other, you need to have a boundary point that's part of one and not part of the other, but neither one of them contains its boundary points. So two open in the topological sense, right? Can't come into contact. All right, also, this is the more interesting one from this point of view, two closed objects can't come into contact either. So imagine two cubes that both include their boundaries. Those can't come into contact for Hudson, because if they did, they would have to share their boundary, and he thinks that two objects, at least certain kinds of objects, can't interpenetrate. They can't share anything. And so that's not possible. So it's not possible for an open object and two open objects to touch each other, because neither one has its boundary points, and it's not possible for two closed objects to touch each other because the objects can't overlap. All right, now here's the knot. All right, so suppose that two closed cubical objects are moving towards each other at a constant velocity. So we've got two cubes, ice cubes say, both that contain their boundaries, and they start moving towards each other at a constant velocity. And suppose they're oriented so a side of one of them is parallel to a side of the other one. So they're headed to contact. Suppose they start out exactly 5 meters from each other. Oh, that's a typo here. One of them moving at 1 meter per second relative to the other. All right. Now, what happens as you get close to the 5-second limit? When they're about to come into contact. The objects cannot end up touching, because, on his view, because they can't. Right? They can't touch. They can't overlap. Right? All right. But no matter how close they can always get closer. So what happens? All right. So of course, in the actual world, no object can occupy a closed region. Right? We know that from physics. Matter of fact, no object occupies. Again, my quantum mechanics is rusty. There's different interpretations of it. But generally, no object occupies any region sharply. What you have is a probability density that fades off, and those can overlap. All right. Moreover, the particles that make up each object, and even if the world was more Newtonian, the particles that make up the object have repulsive forces, so they can't come into contact either. But again, we're not dealing with those worlds. We're dealing with this, All right. But here we're supposedly exploring metaphysical possibilities. So now Hudson explains what the problem is, what the knot is. With the exception of pairing a closed object with an open object, that one would work, by the way. Right? So if I have a closed cube and an open one, they fit together exactly. Right? So that's fine. Right? But anything else is not fine. Right? All right, any other pairing can be so oriented that both interpenetration, where they share some of their regions, and touching are not options. The items paired must either slow down, jump, stop, turn, or otherwise deviate from their courses. Given the discussion above, if you buy it all, we can clearly explain that such deviant behavior will occur, but just what explains why. Why must approaching objects change speed or direction? I don't know. that's what the title of this section advertises, a knot rather than a knot untied. All right, so that's Hudson. All right, now, no, I don't know of anybody that has that radical view of receptacles that he does, but the problem that he raises, the knot, I think is a problem for lots of views. Achille Varze, again, it was a nice mathematically informed instance of descriptive metaphysics. I think that's what he claims that he's doing. Focuses on matters of contact and boundaries. So he's wondering what contact is like and what boundaries are like in our conceptual scheme. All right, the world of everyday experience is mostly a world of physical things separated in various ways from their environment. Right? The observation is correct. Aristotle accommodates it well, I think. Things with surfaces, skins, cross boundaries of some sort. Right? Objects generally have boundaries, surfaces. These may not always be sharply defined, sometimes, like clouds. It's not clear just what the boundary is. But other times it seems okay. Generally, boundaries seem to belong to the palette of basic ontological tools which we commonly describe the middle-sized reality of ordinary experience. All right. Oh, this is a long quote. I don't think I need the rest of it. All right. So much of Varze's article, right, going on to the bottom of this page, is a response to what he calls Peirce's puzzle. I don't know if there's any Peirce scholars here. I don't know if Peirce ever discussed this or what he had to say about it. All right, but anyway, here's the puzzle, as Varze puts it. What color is the line of demarcation between a black spot and a white background? You imagine a piece of paper, right, with a black spot on it, and then what color is the boundary of the spot? Takes that to be a real question. That's what I think how Aristotle would answer it. Dumb question. Right? The boundary is just part of the spot, right? You know, so the boundary that's part of the spot, right? To that extent, it's black, but it's also part of the background. To that extent, it's white. But Aristotle would insist that the boundary isn't this separate thing, right? You have to attribute to one or the other, right? But anyway, Aristotle was not in the Dedekind Cantor picture, you know, trapped in that like Varze seems to be. All right, take any entity X. Again, this is another quote from Varze. Does the boundary belong to X or to the complement of X? Does the boundary inherit the properties of the object or those of its complement? In a way, if you think about the science of this thing, it's you know, I mean, a boundary is like a point. Points can't have color. All right, Varze argues that at least some instances, now he argues that at least some cases, the answer to the Peirce's puzzle is straightforward, right? Again, in our conceptual scheme. We may find good reasons to maintain that material bodies such as stones or soap bars are the owners of their boundaries. So if you think of like a stone or a bar of soap, right, natural to think that the boundary belongs to the soap and not to the air. Thus, where the complement meets an object of this sort, it'll be open. That is, when the air meets the soap, right, the air is open and the soap is closed. We may also argue that material bodies such as holes are not the owners of their boundaries. Now think of like a donut. Right? The hole of the donut, right, doesn't own its boundary. The boundary belongs to the donut. These belong to the, thus where the two meet, the complement is closed and the entity open. That is, the complement is the air, right, the hole, and the object is the donut, that's open. No, the entity is the hole, that's open, and the donut is closed. All right. Now, there are some analogs of Hudson's knot here. Imagine two objects, both of which include their boundaries. Say a baseball and a bat. Right? Pitchers and catchers reported yesterday, so this is quite relevant. All right, so consider two objects that both include their boundaries intuitively. Remember he said bars of soap, right, include their boundaries, rocks do, so presumably so do baseballs and so do bats. Right. Now suppose the ball is thrown toward the bat is swung and makes contact with the ball, and then goes off to the outfield. All right, now when that happens, at the moment of contact, what happens to the boundary of the ball and the bat? Right. It follows from a suggestion that Varze makes elsewhere, later on in the article, that what happens then is that at least one of the boundaries gets pushed aside so that the other one can fit in there. Right. Now, he concedes that some of the issues are difficult, but he suggests that this is not due to the notion of contact. Oh, here's another example. I don't know if I skipped it or if it's in the slides. So again, think of like a bar of soap again, and we'll assume with Varze that it does include its boundary. And then think of a body of water right? And, you know, like a lake, and we'll assume that that includes its boundary. Or if you want, it doesn't matter, you can think of the boundaries belonging to the air, right? But, all right, now, we put the soap on the water and it floats. Now, the water is closed and the soap is closed. So how can, you know, so what goes on there? Again, Varzy's view would be that the boundary of one or the other of them gets pushed aside so that the other one boundary can fill it in. All right, now part of the problem here, right, that I think Varzy is getting into, and it's certainly part of the problem that I think Hudson's getting into, is that they're thinking that the boundary of a closed object is made up of the same kind of stuff as the rest of the object. That's why Hudson thinks that you can't have interpenetration, because he's thinking of the boundary as the same kind of stuff, is composed of the same kind of stuff as the inside of the object. Now, some metaphysicians, obviously we're not in the contemporary scene anymore, with Suarez, you know, 16th century, Brentano, all right, that's, well, 1988, but you know, but that's just when the thing was published, or the thing that I took it from was published. Brentano would have been late 19th century, and Chisholm. Now he's more or less contemporary. Now they hold that every extended three-dimensional object has a boundary consisting of point-sized parts. All right, so they claim that every three-dimensional object has a boundary that's composed of point-sized parts. The boundary is, and such that two objects are in contact with each other when they share their boundaries. Right, so they don't buy, those three don't buy the Hudson view that they can't interpenetrate. Two objects can share their boundaries. And that's how he would solve the problem with the soap floating on the water. They share their boundaries. Right, now, Suarez and Brentano, at least, not quite sure about Chisholm, held that, as Zimmerman put it, the three-dimensionally extended parts of the thing are not made up out of indivisibles alone, points alone, but also contain some atomless gunk. So the metaphysical picture they have is that the boundary consists of these point-sized things, and there's also some gunky stuff in the middle that fills the object. The boundary points of different objects can coincide, right, like the soap on the water, but the internal parts can't. The gunky stuff can't. But the interior gunky parts can't coincide. Okay. Now that resolves Hudson's knot, or at least that much does. But there are further problems now for this view. Problems that the three of them have addressed, that is Suarez, Brentano, and Chisholm addressed. The reason why it resolves Hudson's knot is that, yeah, they actually come into contact because their boundaries are overlapping, but they don't have to worry about the contact going any further because the gunky stuff is going to keep them from interpenetrating any more than that. All right, now consider any cubical object, say an ice cube. I don't know why I'm hung up on that, especially given how cold it was in Ohio. But, all right, now there's a plane surface within the object that separates the left half from the right half. So take any cubical object and think about a plane that's sort of down the middle of it. According to Suarez, Brentano, and Chisholm, that plane is an interior boundary to the object. And it also consists of point-sized parts. Indeed, there are point-sized parts located everywhere inside the object, along every plane that can divide the object. Presumably, there are a continuum of many such interior potential boundaries. You know, if you bring in the contemporary, Suarez wouldn't have known about it, but the others would. Well, maybe not Brentano. Certainly, Chisholm would have known about it, right? That's how many interior boundaries there have to be. And for at least Suarez and Brentano, that all these internal boundaries, these pointy things inside of it, that's in addition to the gunky stuff. So it's kind of crowded inside the ice cube. Right? Now, how many? Now, take a point inside the ice cube. How many interior boundary points are there at that point? Right? Now, Suarez held just one. And Zimmerman Dean Zimmerman points out that this thesis is awkward and even has preposterous consequences. The idea that there's just one boundary point inside the object at each interior boundary. Now, it's because suppose our cubical object is cut along that plane. And now we've got two. Right? Where do the boundaries of the new part come from? Right? Well, they had to come from the one we cut, right? But there's only one point there. Right? So the separated parts, so where did the point-sized parts of the two faces come from? I think Suarez's view was that the original boundary is destroyed when you do that, and two new boundaries are created. All right, now Brentano and Chisholm held instead that now remember, where each internal point inside the cube has infinitely many boundary point objects there. So when you cut it, half of them go to the one part, and the other half go to the other part. Now you can't just say two, because you might cut it this way and then cut it this way, right? So you need at least four. You can cut it this way, this way, this way. You can cut it continuum many ways. So there's got to be continuum many distinct boundary points at each spatial point. So it's really crowded. In addition to all of those, there's also the gunky stuff. Now let's go back to Brentano. Now he complained. One of the earliest, I'm really interested in this. I wish I knew the history better. What are the precursors to the Dedekind-Cantor view? I mean, where do we get that idea? I mean, it's really orthodoxy nowadays, and we're not claiming, Jeffrey and I aren't claiming that it was a dumb idea, a mistake that the community, I mean, that, no. But it seems to have come out of the blue, and now everyone buys it. But what were the well, one of the precursors to it was Bolzano, 1830s, I guess, right? Yeah, 1830s, right? But he wasn't, in his lifetime, wasn't all that well. I mean, we can't call that an influence, because I don't think he was all that influential. But at least among mathematicians, but certainly the philosophers knew about him. And he had this sort of Dedekind-Cantor picture, I mean, obviously he didn't call it that, where space is composed of points, an actual infinity of points, and objects are like that. And so he actually got stuck with Hudson's knot, and he solved it in the way that Hudson would, right? So that is, so according to Bolzano, the only way two objects can come into contact is if one is open and the other is closed. Right? And Brentano said that that's monstrous, that thought. So this is a quote from Brentano. That Bolzano, again, a great mathematician, right, he's not denying that, but was led to his monstrous doctrine that there would exist bodies with and without surfaces. Right? You're kind of stuck with that.